Alright, now this here is a very nice little question from GATE 2025. A very nice question, honestly. I've been thinking about this question for quite a while. It sort of randomly pops up because I kind of did not realize the beauty that is kind of hidden within the graphs themselves. So let's go over this. It's a very nice little question. It's very easy to get wrong as well, so that is the reason why I'm kind of excited to do this, even though I kind of want to sleep. But let's go. So let G be an edge weighted undirected graph. So it's an edge weighted undirected graph. Okay, so no arrows, nothing, just weights with positive edge weights. Okay, so positive weights only. Suppose a positive constant alpha is added to every weight of the cycle. Oh sorry, to the weight of every edge. Oh my god, my sleepiness. Which one of the following is true about the minimum spanning trees and the shortest path in G before and after the edge weight? Okay, so they are asking what happens with the minimum cost spanning tree and what happens with the shortest path. Now here's the thing, right? I think we can start this discussion by immediately eliminating a couple of things, right? So that is not supposed to be a B, that is supposed to be an H, right? Okay, that is kind of moronic. So I can make any kind of a weird haphazard little nonsense situation here, and I can give them any weight or whatever I can, right? And I think you should immediately ask, so how do you make an MST? What is the process? Now to make an MST, you basically would follow either Kruskal's algorithm or you would follow Prim, right? These are the only two procedures that you would actually follow. Now think about it like this. If you have a set of numbers, right? So let's say 1, 2, 3, 4, right? And I asked you what is the average of these numbers, right? What would you say? You would add these up. So 1 plus 2 plus 3 plus 4. Or wait, is this even a good example? I feel like this may not necessarily be the best example, but okay. Maybe this is not the proper example. So think about it like this. Basically what is happening here is that if let us say we will just consider it like this. So 1 2 3 4, let look at A. Okay, let's just analyze things with respect to A for now. So look at what happens with this guy. So when you say 1 2 3 4, right, and you say that okay, I have to make a move, I have to make the cheapest move possible, right? So it will clearly go from A to B, there's no doubt in that. Okay, now let me ask you, so what if every path now cost 100 extra? So this path now is 104, this path is 103, this path is 102, and this path is 101. Which path will A take now? Well, guess what? The 100 kind of cancels out because everyone has 100, right? In a sense, if you can think about it like that. But this one kind of just stays, right? So 1 2 3 4 kind of effectively still remains the same way as it is. The order doesn't necessarily change, right? And you can just still would actually choose A to B because that is still the cheapest, right? So essentially, because of the way that Prim and Kruskal work, where they're not necessarily sort of affected by these kind of changes that happen to every single edge. If you think about the method in which they operate as well, Kruskal and Prim, you can add whatever constant you want, and Kruskal will still arrange everything in ascending order. And if in ascending order a particular edge was in the first, after adding 100 to every single edge, it would still be the first, right? So that's like saying 1 2 3 4, and if I add 100, the order will change. Hell no, it won't change. 1 2 3 4, if you add 100 to everything, it will become 101, 102, 103, 104. The same edges will still exist, and therefore any MST made by Kruskal will still be the same that it was. It won't necessarily change. Now consider Prim as well. Now with respect to Prim, it is still doing the exact same thing, where you just give it the particular name of the edge to start from, and then it would just basically do the same thing, where it would pick simply the cheapest ones possible, and its job is to simply connect the edges. It's not trying to find the shortest path, it is simply trying to connect everything. And you can go ahead and try a couple of examples. Prim would also basically end up with basically any MST that is made through Prim would also still remain a MST right after this whole process is done as well. So therefore we can immediately exclude any of these MST need not remain options. They're dumb. The fun part is when you actually consider the shortest path one, because that is where craziness can actually happen. Let me take a nice little example. So you take A, B, C, D. Okay, let's take this example. let's say that this is the graph. What is the shortest path here? So let's say I only care about getting from A to D. So I have two paths, ABD or I have ACD. Now if I go through ABD, I would take 1 plus 2, which is a 3. If I go through ACD, I would take 3 plus 4, which is a 7, right? So notice how ABD is in fact the shortest path here. Now what if I add 100? Notice what happens if I add 100, right? So let me just quickly draw the graph again. So 101, 102, 104, 103. So ABD now becomes 101 plus 102, which is in fact 103. ACD now would become 107. So still ABD remains, right? So now you might feel very much inclined to actually select every shortest path also remains a shortest path. But I would ask you, have we actually done any kind of a discriminating kind of a thing here? And I think you should say yes immediately, because notice how in the question nowhere did they mention that the edge weight has to be unique. They never said that. We were the ones that assumed it, and that is why I quietly labeled it as case 1, right? Because in this particular case, sure, every SP remains an SP, right? So every shortest path will remain a shortest path, that is for sure, no problem. Let me make a new page instead of continuing here. Now the second case, then you might say that okay, let's go aggressive, right? So let's take the exact same thing, right? And now this time we'll give everything the same weight. Okay, so ABD, ACD, if we count the edge weight, it will be 2 2. Now if I add 100 to everything, it won't really make a difference, because now it will just cause 100 and 102, 102. So every SP is still an SP. Whoops, every SP is still an SP, right? So even here now with this particular thing, you are still actually discriminating again. Is it really the case that you cannot have a hybrid, a mix of distinct and non-distinct edge weights, right? So that is the third case that you're actually missing out on, right? So let's make a nice little example here. So A, B, C, D, and I'll make this, right, F and that. Let's say 1, 2, 2, 3. So let us say this is 7. Okay, yeah, let us say this is sort of what the situation is, or you know what, I'm ready to make it even worse for this one. Yeah, let's make it extremely bad. So 10 plus 10, yeah, let's do that. Now if I ask you what is the shortest path here, A, B, C, D, it would be 1 plus 2 plus 3, which would be 6, right? If I ask you what is the shortest path through AFD, like if I again I'm trying to reach to D, so let's just manually check, right? 20. Awesome. Now notice what happens if I add 100 to everything, right? If I add 100 to everything here, you would get 101, 102, 103, yes, and F would become 100 and 100 actually, just 110. What am I doing? And this would also become 110. Now notice, right? So if I write ABCD, the cost of ABCD now is 306, whereas the cost of AFD is now in fact, guess what, 220. Did you notice what just happened? So earlier ABCD was the shortest path. Now ABCD is no longer the shortest path. It is now AFD, right? It has changed. Earlier it was the longer path. Now it is the shortest path. And therefore through such a simple counter example, you can actually see a very, very neat property that, while being greedy kind of actually works, where you actually take the shorter path and you make the locally cheaper choice. That does not mean that if you have the same configuration, but then the or rather, let me say it this way, if you have the same graph but the edge weights are basically changed like at some crazy level, it doesn't mean that the shortest path that you had earlier is still the shortest path now. You can very clearly see what has happened here, right? It basically seems like for every hop that you have made, you were penalized quite a bit heavily, right? Because look at this. So you took two nice little hops here, or instead I should say you took three nice edges here, and because of that your penalty is 300 right? And then the regular cost would have been 6, and then here you took 2 edges, and therefore the penalty was 200 and then 20. So notice how using Dijkstra is good, right? It's actually a very good algorithm, but in these kind of bizarre cases where you have one cost at the starting, and then after running, or while you're in the process of running, the edge weights upgrade or update in a drastic fashion, what ends up happening is that these kind of edges that you earlier would kind of have ignored because they do not get you to the path quicker, you actually prefer, because they actually are using lesser number of edges. So as the cost increases, you start preferring edges. Now you start preferring paths with lesser number of edges. Okay, so if the cost is cheap, you go for more edges essentially, and if expensive, right, you go for lesser number of edges, right? That is basically what this whole kind of idea is actually pointing at, and that is why you have to really look at this whole thing and say that what, every MST will not remain an MST. Every SP will not remain an SP, right? So C is in fact the correct answer, that every MST will in fact be an MST, that is fine, but SPs will not remain an SP, right? We clearly saw this very nice little example here, and it's a very nice idea. You can kind of think about it, right? Because it's like you had to earlier, it's like this: if you had to use connections to get somewhere, right? If they are your current friends or something like that, it'll be quite cheap in some sense, right? Like you can just ask them or something like that. But then there's this distant relative or someone who can get you there. It might feel much more expensive in some way. I don't know what I'm getting at, but the point is that when it takes a lot more effort to do a certain thing, you would prefer a path with the lesser number of sort of nodes to travel, in a sense, right? That is kind of what it is. I don't know if I'm trying to become like philosophical or what, but yeah, that basically is the summary. It was a beautiful question. I really have been thinking about this question quite a bit. Made me really enjoy algorithms and just graphs in general. So yeah, that was about it. See ya.